Hello and welcome to the remediation video that will cover the essential standards that you need to know for the nuclear chemistry unit. As you see from the title slide, we will be going back over radioactive decay, and we will also be looking at the concept and the calculations that are involved with half-life. In order to be ready to engage in this video, you will need note-taking materials, and then following the video, you will need to, if you haven't yet, print the homework assignment that goes along with the video and complete that and check your answers, which are also available online. So again, today we are going to be looking at decay and at half-life. So why don't we start with decay first? When we talk about decay, we're talking about the process where unstable atomic nuclei break down, not break apart in the way that they do with fission, but they are breaking down. And as they break down, they release small particles, and these small particles are what we call radioactivity. What you'll find is that there are actually many different types of decay, probably a dozen or more. Of these, you only need to know three. You need to know alpha decay, beta decay, and gamma decay. And we are actually going to talk first about gamma decay because it is the one that is not a particle and therefore the one that you need to know the least about. Gamma decay, again, is not a particle. Instead, it is actually a form of high energy waves, not unlike light. It's also a part of the electromagnetic spectrum, but because it's not a particle, it doesn't change the makeup of the nucleus, and as a result, you just need to know that gamma radiation does not change the atomic mass or the atomic number of the nucleus. It's simply the release of energy. The two types of radiation that are particle radiation that you need to know are alpha and beta decay. And so we're going to go over both of those next. We will talk about, first of all, what they are, and then we will get into the details of how they change the nucleus of the atom. So let's talk about alpha decay first. When we talk about alpha decay, you'll notice that we abbreviate alpha decay with either a HE 4/2 or the Greek symbol for alpha, actually lowercase alpha, which is the curly Q that you see right here next to the HE 4/2. Probably the one that you'll want to keep track of is the HE 4/2 because that tells us more about how it changes the nucleus of the atom. So when we talk about alpha decay, we are actually talking about the release of a helium nucleus. Looking at helium and seeing that helium is He 4/2, that tells us that a helium nucleus is 2 protons, that's the bottom number, the atomic number, and then its mass is 4, which tells us that it's got 2 neutrons. So a helium nucleus is actually 2 protons and 2 neutrons bound together. And when a packet or a package of 2 protons and 2 neutrons leave the nucleus of an atom, we call that alpha decay. When this happens, these particles that are released are big, low energy, slow particles that are not very penetrating. But as this happens, the thing that you need to know about how it affects the nucleus is the atomic number Z during alpha decay goes down by 2, and the atomic mass A goes down by 4. And again, we need to remember that Z, the atomic number, tells us the number of protons, and then A, the atomic mass, tells us the number of protons and neutrons. So what does this look like when a nucleus goes through alpha decay? Well, let's take a look at what happens when oxygen-16 goes through alpha decay. And what we're going to do is we are going to, first of all, represent oxygen-16. So that's element 8, oxygen, with a mass of 16. The question is when oxygen-16 goes through alpha decay, what particles are formed? So to represent this, we are going to allow these circles to represent the nuclei of the atoms that are involved in this process. So first of all, let's represent the nucleus of an oxygen-16 atom. And that would look something like this. You'll notice that we've got 8 red protons. That would make this element number 8. And then we've got also 8 neutrons, and we know that's how many we should have because 16 minus 8 is 8, which tells us that we should have 8 neutrons. Now the question is, what will happen to this oxygen nucleus when it goes through alpha decay? So when we talk about alpha decay, we are talking about 2 protons and 2 neutrons quite literally coming out of the nucleus. And if you watch carefully in the lower right-hand corner of this oxygen nucleus, you will see that alpha particle come out of the nucleus. Literally, it leaves. This is a helium nucleus, which we call an alpha particle. And again, the idea is that the 2 protons make it helium, and then the 2 neutrons give it a mass of 4. So that would be our alpha particle. So the question then is, what's left? Well, the particle that's left is now missing 2 protons and 2 neutrons. So if we count protons, we have now got, and we'll do this in blue, we have now got 1, 2, 3, 4, 5, 6 protons. So this is now element 6, which is carbon. Now we need to know the mass of this, and in order to figure out the mass, we're going to count all of the particles. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would now be carbon, element 6, with a mass of 12, and the particle that came out would be an alpha particle, which would be helium 4 over 2. So what might this then look like if we didn't draw the pictures? Well, if we're not drawing the pictures and not looking at the protons and neutrons as we've drawn them, how do we know that when an alpha particle comes out that we're left with carbon 12? Well, look at what happened. The atomic number, oxygen as 8, went down to 6. So the atomic number Z went down by 2, and then you'll notice that the atomic mass, which started as 16, went down by 12, or I'm sorry, went down to 12 by decreasing by 4. So you'll see that the atomic number Z went down by 2, and the atomic mass A went down by 4. That's what we mean by the rule of thumb, where Z goes down by 2 and A goes down by 4. So whenever you're predicting the products of alpha decay, you just need to take the bottom number Z down by 2 and the top number A down by 4, and then whatever this new element is, based upon its new atomic number Z, is the abbreviation that you'll put in front, so, or behind that. So this is alpha decay. Now let's talk about beta decay. Beta decay is actually the release of an electron through the nucleus. So I really don't think you need to worry about its Greek abbreviation. Just realize that beta decay we represent as E minus 1. So what is this electron that comes out of the nucleus? Well, it's kind of an exotic electron. This is an electron that comes out of the nucleus when a neutron becomes a proton. So quite literally, a neutron in the nucleus becomes a proton, and when it does, it releases an electron. These electrons, however, are very small, high-energy particles. They're much more penetrating than alpha decay, but they are very literally an electron coming out of the nucleus. So when an atom goes through beta decay, what does that do to the nucleus? Well, we've got a rule of thumb. What happens is Z, the atomic number, goes up by 1 because a neutron becomes a proton, and Z tells us the number of protons, and then the mass doesn't change, and you'll find out that's because neutrons and protons weigh the same. So let's take an idea what this looks like. So let's go back again to our oxygen 16 atom, because we're already familiar with that, and let's look at what happens when this goes through beta decay. So again, here's our oxygen 16, and we're going to figure out what this forms when it goes through beta decay. Now again, we're going to allow these circles to represent the particles that are involved in the process. So here again is our oxygen 16 nucleus. Again, notice that there are 8 protons and there are 8 neutrons, and that gives this thing a total mass of 16. Now, keep your eye on this neutron right here, the bottom right-hand corner, that neutron right there. And as you watch that neutron, we are now going to have this nucleus go through beta decay. And when it does, watch what happens to that neutron, because quite literally, during beta decay, a neutron turns into a proton. And when it does, it releases an electron. And so in order for us to represent that, we say that an electron has been released from this nucleus. But when it does, look at what is then formed. This is our other product. And if we count the number of protons, you'll notice that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is no longer oxygen, element 8. This is now fluorine, element 9. Now to figure out what this atom weighs, let's count up all of the particles. So when we figure out its weight, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So its mass is 16. So comparing that to what it was before, you'll notice that its mass hasn't changed. Neutrons and protons weigh the same, and so its mass hasn't changed at all. But look at what happened to its atomic number Z. It went up by 1 because a neutron turned into a proton, and the atomic number Z tells us the number of protons. So this would be beta decay. So again, it's nice to be able to see those pictures, but the question is, how do we do this when we don't have the pictures? Well, now all we have to do is keep in mind our rules of thumb. So you'll notice here in this first example, as we follow the arrow from left to right, we go from xenon to cesium. And you'll notice again that the top number A is staying the same, and the bottom number Z is going up by 1. So what type of decay is it, alpha or beta, that causes the mass, the top number, to stay the same, and the bottom number, the atomic number, to go up by 1? Well, that is beta decay, and when we represent a beta particle, we do it like that. So now let's take a look at our second example. I'll switch colors so we don't get confused. So now we have a type of decay where the atomic mass on top goes down by 4, and the atomic number on the bottom goes down by 2. This is the rule of thumb for alpha decay, and so to represent an alpha particle, we put helium 4/2. So that would be a classic example of alpha decay, where the bottom number Z goes down by 2 and the top number A goes down by 4. Now let's clean up our mess and let's look at our last example. Now you'll notice they've given us the type of decay. Helium 4/2 is an alpha particle, and we need to figure out what the products are. Well, we know in alpha decay, the bottom number, which is originally 92, goes down by 2, it goes down by 90, and then the top number, 238, goes down by 4, so that would become 234. Now we need to figure out what element that is, and by looking at our periodic table, we see that element number 90 is thorium. So if you don't yet have your periodic table out, I would encourage you to grab it and check and make sure that you see that element number 90 is thorium, and that would be the product of that alpha decay. So we can see these like this, but another way that we've seen these alpha and beta decays represented are where they give us not even the formulas of the starting particles. So for example, here it says when radon 222 goes through alpha decay, what does that create? And in order to do that, we know that radon is Rn. Again, looking at the periodic table that you just got out, radon has a mass of 222. That's the number here. And then radon is element number 86. Now the question is asking, what does this turn into if this goes through alpha decay? Well, again, an alpha particle is helium-4 over 2, so the bottom number, 86, goes down by 2 to 84, and the top number, 222, goes down to 218. Bottom number down by 2, top number down by 4. Now we need to figure out what element 84 is, and that would be polonium, and that would be the result of that decay. Now to do a beta decay, we're looking at the beta decay of bismuth 214. So we find bismuth on the periodic table. Bismuth is element 83, I believe. Yep, bismuth is 83, and in this case its mass is 214. So the question then becomes, what does this turn into when it goes through beta decay? Now remember, in beta decay, a neutron turns into a proton. So the bottom number, the atomic number, goes up to 84, and the top number, the mass, does not change because, again, neutrons and protons weigh the same. But because the atomic number went up by 1, this is no longer element number 83. It went up to element 84, and interestingly, that is also polonium, element number 84. You'll notice that as we've been going through these, we have not done decay representations for gamma decay. Again, the idea is that you won't be asked to do that because gamma decay does not change the nucleus of the atom. It's merely the release of energy, and as a result, you just need to be able to do this type of process for alpha and beta decay. So those are the things that you need to know about alpha and beta and, well, the radioactive processes. Now what we need to talk about is half-life. As we've been talking about this idea of how these things decay, we also need to be able to talk about how quickly these decay processes happen. Now the problem is that there's no way for us to know when a particular atom will go through radioactive decay. So instead what we do is we talk about averages. And the average that we talk about is half. So when we measure the speed of radioactive decay, we do this in half-lives. And half-life is the amount of time that it takes for half of the atoms in a piece of radioactive material to break apart. Now it's important that you understand that after these atoms go through alpha or beta decay or any other type of radioactive decay, they don't just disappear. So after each half-life, 1/2 of the original sample remains, and the other half has become another element. So when we take that idea and look at it graphically, it looks like this. So the idea is that we are going to look at the decay of whatever this element is that is represented by red circles. And you'll notice that down across the x-axis, we've got the number of half-lives, 1, 2, 3, 4, and so on. And then what we're going to do is we are going to look at what percentage of the sample remains, but these percentages will also be represented by the number of red circles that exist in the drawing at the top. So the idea then is this, that if we start with 100 red circles, after 1 half-life, 50% of those red circles still remain, and 50% of those red circles have turned into gray circles. So after 1 half-life, if we start with 100, after 1 half-life, 50 red circles are left, that's half, and then 50 of those red circles have turned into gray circles. So what about after 2 half-lives? Well, now what we're going to do is we are going to take half of the half. So after 2 half-lives, we will cut the 100 in half twice. So after 1 half-life, we've got 50 left. After a second half-life, we now have 50 divided by half, which leaves us with 25%. Then after another half-life, if we have 25 here, we'll then cut that in half again, going down to 3 half-lives, and that actually leaves us with 12.5 red circles, Unfortunately, they did, I think, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It should actually be 12 and a half because it would be another half of a half. So the way that this progresses then is after one half-life, you have 50% remaining. After two half-lives, you'll lose another half of the half down to 25%, and so on. So while we've looked at this conceptually, we now need to look at this mathematically. And when we look at this mathematically, these are the equations that we use to represent this. So as we look at this mathematically, the equation on the left allows us to figure out how many half-lives a substance goes through in a given amount of time. So say, for example, we have a substance and its half-life is 10 years. So a half-life for this substance is 10 years. And say, for example, that this substance sits around for 40 years. So the 40 would be the number of years that this sits around, and then time 1/2, which is the time of a half-life, would be 10 years, and 40 divided by 10 is 4. So the number of half-lives would be 4. So the idea is that if we want to calculate how many half-lives a substance has gone through, we need to know the time of a half-life, and then we need to know the time that it sits around. And so again, if we have a half-life of 10 years, and if it sits around for 40 years, that would be 4 half-lives. The equation on the right then allows us to figure out the percent of a sample that remains. And so as we think about percent remaining, the progression goes like this. So we could have 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, and 5 half-lives. So after 1 half-life, we will have 1/2. Let me clean that up. So 1, 2, 3, 4, 5. So after 1 half-life, we will have half of the sample, or 50% remaining. After 2 half-lives, we'll have 1/4, or 25%. After 3 half-lives, we will have 1/8, and then 1/16, and then 1/32, and so on. So the question is, where do these numbers come from? Well, the numbers come from this equation. So if we plug the number of half-lives in for n, that will then tell us the percent of a sample that remains. So if we plug in 1, 2 to the first power is 2, that leaves us with 1/2. If we plug in 2, 2 to the second power, remember this is an exponent so it's squared, would leave us 1/4. If we plug in 3, 2 times 2 times 2 is 8, so that would leave us 1/8. If we plug in 4, 2 to the fourth power, which is 2 times 2 times 2 times 2, is 1/16. And then if we plug in 5, that would be 1/32. So this equation on the right allows us to calculate how much of a sample remains. So what we can do then is we can use these two equations to solve two types of problems. You may remember from class that there were many different types of half-life problems that we could have solved. Well, we are only going to ask you to be able to solve two different types of problems. One of these problems will be mass remaining problems, and then the other type of problem will be a problem where you're calculating half-life. So let's first look at a problem where you're figuring out the mass remaining. Reading the problem with me, it says 50 grams of plutonium decays for 72,000 years. What mass of plutonium remains at the end of this time? And we remember that, well, we remember from the Bill Nye video that the half-life of plutonium is 24,000 years. And understand, you really don't need to remember the half-life of plutonium. These numbers will be given to you. Okay, so how do we solve this problem? Well, the first thing that we will always do is write down our equations. Then what we need to do is figure out what information we've been given. So we've been given 72,000 years. And it tells us that that is the time that this substance sits around and decays. Then it also tells us 24,000 years is the time of a half-life. Now we need to figure out what we're solving for. And you'll notice in the second sentence, it says, what mass of plutonium remains? So we're trying to figure out the amount remaining, which is essentially the percent remaining. So our goal is to solve for the percent remaining. Now to do that, we need to know n. The problem is it doesn't tell us the number of half-lives. So we're going to come over here and we're going to solve for that here and then plug it back in. So pulling this all together, we are first of all going to realize that we're solving for percent remaining. So to do that, we need to know n. But we can solve for n because we know that the sample sits around for a time of 72,000 years and a half-life is 24,000 years. Dividing 72,000 by 24,000, we find out that we went through 3 half-lives in that time. That number, 3 half-lives, then gets plugged in over in the right-hand equation, and we now know that our percent remaining is 1 over 2 to the third. Now be careful, because 1 over 2 to the third is not 6. This is an exponent, so it would be 2 times 2 times 2, or an eighth. So we know that our percent remaining will be 1/8. But it's 1/8 of the 50 grams that we originally started with. So if we take 50 grams and multiply it by an eighth, that would be 6.25 grams. And that would be the mass remaining, which is what we're actually solving for, the mass remaining of plutonium. So that's one of the types of problems that you need to be able to solve. You'll be given the time of a half-life, and you will be given an amount of time that the sample decays, and you will be given a starting mass, and you need to figure out the mass that remains. The other type of problem that you'll need to solve is a problem where you are being asked to solve for half-life. How long is the half-life of a sample? So for example, it says 100 grams of molybdenum-91 decays for 60 minutes. At the end of this period of time, 6¼ grams of the molybdenum-91 remains. What is the half-life of the isotope? So in this problem, we're given a starting mass, we are given an ending mass, and then we are given the time that the substance decays, which is 60 minutes. The question is, what is half-life? What is the half-life of this substance? So again, to figure this out, we need to write down our equations, and now we see that what we're solving for is T1/2. We need to know the half-life. Well, to solve for that, we need to know T, and we need to know N. Now we're given T. We're told that this thing decays for 60 minutes. What we don't know is N. So what we're going to do is we're going to solve this equation for N and then move it back and plug it in over here. So how does that process work? Well, as we solve for T1/2, the first thing that we're going to do is realize we're given the amount of time. That's 60 minutes. What we don't know is T1/2. That's our goal. But to solve for this, we need to know N, and currently we don't. So now we turn our attention to the right-hand equation, and we need to figure out how to solve this for N. Well, in order to solve this for N, we need to know the percent remaining, but we don't know the percent remaining. But what we do know is this. We started with 100 grams, and at the end of this, we ended up with 6.25 grams. And those two together are the percent remaining. We put the small number on top and we put the big number on bottom. And it's always small on top and big on bottom, and that is equal to 1 over 2 to the n. Now we've got to solve this for n. And so the numbers that we pick for you will make this relatively simpler because we will always give you numbers that reduce to orderly fractions. So what we're going to do is we're going to simplify the fraction 6.25 over 100. To do that, we are going to divide by the smallest number. Now remember, the small number goes on top. It will always be small number on top, so you will divide by the smaller number, which is 6.25. Now any number divided by itself is 1, and 100 divided by 6.25 is 16. This is equal to 1 over 2 to the n. Now we need to solve this for n. Well, the numerator is already 1s, so that's great. So now the question is, what power do we need to raise 2 to make that equal 16? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So that means that 2 to the 1, 2, 3, 4, 2 to the 4th is 16. So that means that n is equal to 4. Now what we can do is we can take that number 4 and we can plug it in for our question mark in our left-hand equation. Now to solve this for x, we cross multiply. 4x is equal to 60. Then we divide by 4 and we find out that the time of a half-life is 15 minutes. So again, this is an example of the other type of problem that you will need to be able to solve in the half-life problems. So we have now gone over the things that you need to know about alpha, beta, and gamma decay, and we've gone over the concept of half-life and the two types of half-life problems that you will need to be able to solve. What you'll want to do now is get the homework assignment that goes along with the remediation video and complete it. Then once you're done with that, you will check your answers online, make sure that you've got these answers correct, or importantly, look for the things that you don't understand and then come to one of the two remediation sessions where you'll have the opportunity to get these misunderstandings corrected in preparation for the replacement test. So thank you for watching, and make sure that you get a chance to look at that homework and get your questions answered. Thank you.